Okay, welcome back. Now we'll revise the idea behind parallel plates. All right. So just to note that you should have studied this before. Right. So within two parallel plates, right, normally how it comes about is they are attached to a battery like that, where the positive end is connected to a positive plate and the negative end is connected to a negative plate. Right. And within these parallel plates, right, actually this is the part that we care about. Right, the part whereby the electric field lines are actually parallel to one another, and the implication is that since the distance of the lines are equal distance from one another, that the electric field strength anywhere in between this region is the same. Therefore, if I put a charge here or here or here, right, it doesn't matter. All these charges will have a force equal to QE, right? So they, assuming they're the same charge, right, and inside the same electric field, they must have the same force, right? Doesn't matter where is it A, B, or C, doesn't matter. As long as the same charge, same force. Okay, so that's the idea behind parallel plates. You don't really have to care about edge conditions unless the question specifically mention it. So normally edge effect is ignored in A level, so you don't have to worry about this part. But if you really make a careful observation, you realize that this spacing is normally drawn bigger than the red one because this is a weaker field, right, than inside the parallel plate itself, right? That means in this region. Okay, moving on. Right, we'll try this question here. Right, do pause and try the question yourself. Which one of the squares is in equilibrium? Okay, we're back from the pause. Right, you can see four different charges of on a rigid square on a frictionless surface. Right, so uniform field is applied from left to right. Right, so uniform field again, you need to imagine yourself. It's this thing, right, equal distance apart as part what we have just learned. Right, and this thing is basically acting across the whole space here. Right, so I don't want to draw the field on top because you just mess up the whole diagram lah. But that's what you have to imagine in your head, that this whole electric field is actually existing in this square space. Right. So with that, let's try and figure out which of these squares are in equilibrium. Right. We want to figure out the force first. Right. So remember that electric field is the direction of the force on a positive charge. So on a negative charge, the force must be opposite direction. So if the field is to the right, the force is to the left. Right? So if it's positive charge, then it's to the right. Okay, and you notice I draw this one bigger than the last one because uh, force is equal to QE. If the E is the same, then the Q is double. The force must be double as well. Right? So that's why this force is twice the size of this force. Right? Then I carry on drawing. Of course, minus 2Q, the direction will be this way, and plus Q, the direction will be this way. Right, you can see I try as much as possible draw things that are same size, same magnitude, the same size. Right, so plus 2Q again this way, minus 2Q again this way. Right, minus Q is this way, plus Q is this way. Right, minus 2Q this way, plus 2Q this way, plus Q this way, minus Q this way. Right, so you can see all the answers to this. Alright, then we check what is the condition for equilibrium. Right, there are two things if you remember from forces. Number one, no net force, alright, and no net torque or no net moment. Right, so obviously easier to check no net force first. Is there no net force in A? Yes, because this one balance this one balance this one. So the left force equal right force. If we look at B again, they balance out here and they balance out here. So left force equal right force. C is the same, D is the same. So all of them have no net force. Alright, so I have to check no net moment. Right? In no net moment, traditionally we pick the center lah. You can pick this one. Nothing wrong with picking this one also. Right? But I will just try and do something different. I'll pick a place where I can kill two vectors. The moment of two vectors. Alright, so I'll pick this point instead. If I pick this point, this one got no moment, this one got no moment. Because the line of action passed through the pivot, there is no perpendicular distance. Right? Then the perpendicular distance for plus Q, right? If you don't know how to find line of action, right, then you move your ruler along this dotted line until you hit the pivot here, right? You realize, oh, your ruler will hinge here, come like that. And this, you draw a line, this is my perpendicular distance. You try it for 2Q, is the same, right? They have the same perpendicular distance from the pivot. So minus 2Q times D versus Q times D. right? Which one is bigger? Definitely minus 2q times d is bigger. In fact, it's minus 2q e times d lah, because it should be force times perpendicular distance, right? The force is actually 2qe, right? Remember, because earlier we discussed force is QE, right? So it's 2QE times D, right? But anyway, clearly this moment is bigger than this moment lah, right? So A is wrong. A cannot be in equilibrium. If you look at B, we can test the same concept, right? If I pick here as pivot, these two forces got no moment, only these two forces got moment. Perpendicular distance is the same, right? So yeah, you realize that this one will oppose this, because this one is anti-clockwise and this one is clockwise. So B is the correct answer lah. We can check C and D lah, but you should get the same idea already. Okay, so I won't go on to check C and D. You should check that C and D have moments. Okay, alright? Yeah, that one I'll leave it to do yourself. Right, answer in this case is B. Right, we move on to the next question, question 4. Okay, 4 metal spheres have equal and opposite charge. Which of them is a possible distribution of charge in the sphere and electric field near the sphere? So they're asking you two things. Inside the sphere, how does the charge look like? And the electric field near the sphere, how does it look like? Okay, pause and do. Right, we're back from the pause. Normally, I'll try and look at the inside of the sphere first to try and eliminate clearly wrong answers. Right, if I look at B, B clearly got something wrong because this is the distribution of charges in a sphere, assuming that the sphere is isolated. But this sphere is not isolated, it's interacting with this field. Right, the electric field is actually interacting of one, the positive sphere is interacting with the negative one. So clearly they are not isolated spheres. So the distribution of charges cannot be like that, right? So the positive distribution here needs to be somewhat influenced by negative charges here, right? Then so B is wrong, B is clearly wrong, right? D, you can see that should there be zero field here and here, right? There should be some field still lah. So D is wrong as well, right? It's between A and C because A and C the inside look okay, right? Then between A and C, which one is correct? A is suggesting something to the degree that this one is smaller than this one. That means this is a weaker field. Whereas in C, it's suggesting that it looks a bit like parallel here, somewhere along this dotted line. Right, I can tell you that A is the answer lah. Alright, I'll try and explain to you why. Okay, just based on external field, right? If you look at the field, let's say somewhere exactly in between, right? The field from the positive charge will be towards the left, right, and the field from the negative charge will be towards the right as well, right? Because negative is inwards to the sphere itself. So the vector sum is something like that. Right, what's the magnitude of each of these electric field, right? The formula we learned earlier is 1 over 4 pi epsilon naught Q over R squared, where R is this R. Okay, so the distance from the center of the sphere, because I assume the sphere is a point source, remember that, right? Distance from the center of the sphere to the point in the center, right? If I will consider any point along this dotted line, vertical dotted line, here for example, if I look at the vector of the field from the positive charge, I need to draw a dotted line like that, then I extend this line. Will you expect this line to be bigger or smaller than this one? Right, this is from the positive sphere, this is also from positive sphere. This one should be smaller in magnitude. Alright, why? Because if you look at the formula, Q is the same because same sphere. For 1 over 4 pi epsilon naught is constant, but the R is bigger. So if the R is bigger, right, what happened to E? Field strength? Smaller. So number one, this vector is smaller. Right, I'll draw in black. This vector is smaller. Right, then I'll look at the negative charge one. Right, so negative charge one, again, I try and draw a dotted line like that. Guide me. Right, do you expect this one to be bigger or smaller than this one, which is also caused by the negative charge? Right, again, same thing. This one should be smaller. Right, because same formula. Right, so same philosophy lah. The radius here is bigger. This R is bigger than this R. Right, so this one you should expect the field here is weaker. Therefore, I draw a smaller vector to represent it. Right, so if you think about it, number one, these two vectors are bigger. and they are also summing in the most optimized way because they are in the same direction. Therefore, this vector, the resultant vector, must surely be bigger than this vector, which looks something like that. Right? So this vector over here. Number one, I just call these vectors A and B. I call this C and D. A and B are smaller than C and D. And A and B sum in a manner that is not the maximum way to sum A and B, because maximum way to sum A and B is like that. Correct? So clearly this is a weaker resultant than this one. And therefore it must be shown in the diagram that somehow, okay, I'll erase all this, right? Somehow that along this vertical dotted line, the field here must be stronger than the field here, right? That means it gets weaker and weaker as it goes out like that and like that, right? That means to say this one should be smaller than this one to show that this is stronger, a stronger region of field, right? And that is shown in A, but not shown in C, because in C, it looks the same. It looks equal distance. In fact, this one looks bigger than this one, right? Which cannot be lah. Cannot be this region is weaker than the parts above it, right? So if you wish to read the standard answer, you can pause and read. All right, otherwise, please carry on to question 5. Right, please pause and try yourself, all right? You need to try yourself so that when I go through the answer, you have some learning, right? If you just copy answer, you're not going to learn anything. Okay, we move on to question 5. All right, sketch the variation of electric field strength distance R from a positive charge Q and a negative charge Q. Right, so for this one, it is similar to gravitation. So maybe I'll revise your gravitation with you. Right, you should realize that a lot of your gravitation formulas and this one is similar. Okay, for gravitation, right, let's say this is the Earth. Right, the gravitational field strength, right, will be always towards the center of the Earth, because gravitation only got mass. So what type of mass? There's no positive and negative, right? So if I were to draw the electric field strength against distance, right, the formula is, sorry, not electric field strength, in this case it's gravitational field strength, right, is G m mass of the Earth over R squared, right? So R squared, the curve we should be familiar with, right? But the direction in this region, right, that means to the left of the y-axis, sorry, to the right of the y-axis, should be to the left, right? Because this is the direction. And the direction to the left of the y-axis, right, that means this region should be to the right, right? So if normally this type of thing, we take right as positive because we follow the R direction, right? So if this positive, this is negative, and this is positive, right? So if this negative, how should I draw the graph? Like that. If this positive, how should I draw the graph? Like that, right? So that's how your gravitational field against our graph look like. Okay, because normally we follow the x-axis as convention positive, right? So let's try with a positive charge now. Okay, so if I have a positive charge here, the field direction is out, right, as discussed earlier. Right, I'm not going to draw the rest, but actually, obviously, this region also got field and this region also got field. But I'm just going to draw one dimension, right? Then how to draw the field against our graph? Right, remember the formula is now 1 over 4 pi epsilon naught q, where this q is the positive charge q, right? Very similar to gravitation, over r squared, right? You can see that 1 over 4 pi epsilon naught is the constant, is analogous to the constant g in gravitation. So that's how they are similar. It's almost everything the same, right? So the shape of graph I expect will be very similar. It's just that r in this case is towards the right positive, right? So it defines positive to the right for me here. So this one should be positive because it's also right, right? So the graph should look like that, right? And this one is negative, so it should look like that, right? So you should get the idea already lah. If negative, right, is inward, right? So the same E against R graph, if I want to sketch, should be like that and like that, okay? Because this is positive, right? It's positive. This is negative, right? So this is negative, right? So that's why this one is the negative region, right? Can? Right, let's see if I can push on to one more question. Okay, you can try this question, then, okay, yeah, you can try this question, then we'll come back in the next session to give you the answer, right?